Well, hello again, Blake and Daniel. Good to see you guys today on Zoom. So here is the last, the last of new notes, I believe, unless we actually end up covering a little something extra, but probably this is it. This is certainly the last of the last section in the book. So this is just a little bit on using the divergence theorem. We talked a little bit more about kind of where this comes into play and how it's used. And so the real trick is in the divergence theorem becomes an advantage if it's easy to express somehow somehow express the space that is that is contained within the surface. So if we're looking at our typical double integral of our vector field f dotted with ds, well, if that surface if we can easily express the space that's contained in that surface, then oftentimes it's easier to use the divergence. So we'll go ahead and we'll look at that and we'll see. So if we look at 12, we have the following thing. So we've got this, and we're given our surface here. And so in essence, here's our vector field. So in essence, what we're saying is it would be easier to use the divergence theorem. In this case, since the space that's contained within this surface is just a sphere of radius 1, that's an easy thing to express, so it's probably easier, rather than calculating a normal and taking a dot product and doing all that, it's probably easiest just to go ahead and find the divergence here of f, and then go ahead and calculate using this. So to do that, we know that if this triple integral, because it's going to be of this, is going to be an easier thing to do. Now this one's going to turn out to be really easy, because when I find the divergence of f, derivative with respect to x is 0, derivative with respect to y is 0, derivative with respect to z is 0. So your divergence is just 0, therefore you take the triple integral of 0, you get 0. So that one's pretty straightforward, but it does happen, things like that. So be aware of something like that it can happen in that manner. All right, let's look at some that aren't 0. Let's look at number 14. So 14, we have the following vector field, and we have this surface, which is essentially the surface of the unit cube. So we have the x going from 0 to 1, the y going from 0 to 1, and the z going to 0 to 1. So we think of it as this, surface, which is essentially the surface of the unit cube. Well, the volume of the unit cube is a very easy thing to represent. So it's probably going to be easier in this case to use the divergence theorem. And we'll see that it works out pretty well. So in order to use the divergence theorem, what we have to do is we have to find the divergence of f. So using the divergence of f here, to find take the derivative of this with respect to x, and we just get e to the x, plus the derivative of this with respect to y, which is 0, and the derivative with respect to this, 0. So we get e to the x plus y. I said e to the x, sorry. That's e to the x plus y. And then that just becomes, then our double integral becomes equal to the triple integral of this e to the x plus y over dv. But it's easy to represent the volume here. Okay, the volume, this is expressed in variables x, y, and z. And I see what x ranges to, what y ranges to, what z ranges to. It's pretty easy because it's surfaces. So I know I've got the triple integral going from 0 to 1 for all three variables of e to the x plus y, dz, dy, dx. So now we just go through the process. There's a few, I could have broken this up into e to the x times e to the y and then broken it up into 3 separate integrals. I didn't. I did it this way. Integrate with respect to z. Put in the 1, you get just e to the x plus y. Put in the 0, and you get 0. So that's pretty easy to see that we've got the double integral here going from 0 to 1 for each of them of e to the x plus y. So integrate first with respect to y. And it's a u substitution, but since the derivative of that's just 1, it's just going to be actually, I guess I did break this one up. I could have done it that way. So broke it up now, which then we get the integral of e to the x with respect to x is just oh, I'm missing my e to the x here and my e to the y here. So when I go ahead and plug in, I get e minus 1 times e minus 1, which if I distribute out is just e squared minus 2e plus 1. Okay, fairly straightforward. Now we're going to look at one that is a little bit more complicated because of the surface. So here we've got a vector field, which is actually a fairly complex vector field here. It's not simple. And here we have a surface where we are defining our surface to be z, the value of z greater than or equal to x squared plus y squared, and the value of z that is less than or equal to 8 minus x squared minus y squared. So what we see here is essentially we've got this produces a surface, but contained within that surface, so we get essentially something that is we get a space that's contained within this surface. And so it's difficult. I'm not going to try to visualize that surface. I don't even think the solution manual attempted to visualize the surface. So we're just going to go ahead and solve. What we do see is that we do have an x squared plus y squared, and we see this here. If I factor out the negative, we have 8 minus the x squared plus the y squared. So the nice thing is, though, that's the formula for a circle, so we'll be able to work with that. But we also have z, so essentially we're going to be attacking it like we're going to do cylindrical representation. But the first thing we're going to do is, in this case, the divergence theorem is not as easy because it's not as easy to think about the volume of that space, but we're going to see it's not too bad. So first we're going to go ahead and we're going to find the divergence, which isn't too bad, because if I take the derivative of this with respect to x, I get 0. The derivative of this with respect to y is just 2. The derivative of this with respect to z is 4. So I get 2 plus 4. I get a divergence of 6. So now I can set up my triple integral formula like this. The challenge is coming up with our limits of integration here. That's going to be the challenge as we go ahead and do that, because we have to figure out how we're parameterizing this surface. And it's easiest if since we're going to kind of use cylindrical, if you want to think of it, use cylindrical coordinates, which we know are going to be r, theta, and phi, or theta, r, and phi, however we want to think of it. No, I said phi, sorry, that's spherical, sorry, theta, r, and z. So I'm going to break it up here, and this is going to be the domain of the region in the xy plane, if we want to think of it that way. And this is going to be, so if I want to think of it, this like cross-sectioning it. If I cross-section in the xy plane, this becomes the domain of the region in the xy plane. And this becomes the trapped z, and if you want to think of the height of it, whatever's trapped in between. And so I've got this 6, and then this is z, dz, dy, dx, because this is in terms of x and y here, because it's in, it's that cross section there in terms of x and y, where z is just a constant value represented by this here. So going ahead and doing that, what I'm going to do is I'm going to leave this here to represent z, but I have to go ahead and I have to find out what this cross section looks like in essence. So doing that, the intersection of that cross section there is going to be the intersection here of these two curves. So I want to know what it looks like when they meet and what they do. Remember, this represents a surface, but I'm going to worry about the area in between the surface. So I'm looking at where this x squared plus y squared is equal to this, like that. And I know the z value is trapped between it, but I'm interested in the intersection here between these two. So going ahead and doing this, I get 2x squared plus y squared equals 8, divide by 2, and I get x squared plus y squared equals 4. So what I see is their intersection is actually a circle that is in a plane parallel, as it can move up and down, parallel to the xy plane. and it's a circle of radius 2, is what I see there. But remember, I'm interested in volume. So it's not just the circle there, that's the intersection, but I'm interested in the area trapped inside of that. So I'm actually interested in that disk essentially there. So in order to represent that disk, I know that my radius is 2 and my theta is going to go between 0 to 2 pi. So when I go to represent this, my theta goes between 0 to pi, my disk goes between 0 to 2. Okay, this is the outer region of that. So it goes from 0 to 2. And then notice what I did here is I'm expressing my z in terms of r, since I've got this in terms now of r theta. So now this becomes dz, dr, d theta. And notice because I changed to, if you want to think of it, change this to polar, which meant that I needed to add a factor of r, which we see right there. Or we can think of changing to cylindrical, which means you have to add that factor of r. So with a factor of r, we're set and we can go. So integrating first, well, the first thing I'm going to do here is, so I'm going to integrate that 6r, which becomes 6rz, going from r squared to 8 minus r squared, dr d theta. And what I'm going to do here, I'm going to actually factor this 6 out, put it out here. So I'm going to get 6 times the integral, and I accidentally forgot my second integral here. Let's see if we can change this, since I made a mistake and just didn't write it in. So this is going to be our integral 0 to 2, and we know we are going to have, going from there, we know that we were going to, with a 6 out, we know we're going to have 8r minus r cubed, 8r minus r cubed, minus an r cubed, like that. So we've got this 6. Now what I'm doing is, now I'm breaking it up into 2 separate integrals. So I basically am thinking is 1 times, and this would be 8 minus 2r cubed. So I'm breaking it up into the 1 d theta times the 0 to 2 of the 8r 2r cubed. So integrating this, I just plug in 6 times the 2 theta. And then when I integrate this, I get 4r squared minus 1/2 r to the 4th, evaluated from 0 to 2. So plugging in 2 here looks like I would get 16 minus 8. So I get 6 times 2 pi times 8, which ends up being 96 pi. Okay, hope that makes some sense to you. Here's the last of the assignment here, 11 through 17 odd. So hope that goes well. And yeah, let me know if you have questions. Tomorrow we'll start doing some review from chapter 17.